To all of you watching this video, thank you. Let's continue here with these tests, but this video focuses on, for the first time, a test for divergence. A useful test to know because there are instances out there where doing the test for convergence is cumbersome. Doing the test for divergence would be easier in that case. It's not a difficult test by any means. It's basically just limit applications. If you are good with doing limits, you are good with doing this test. The limit approach or the limit test for divergence is this. You have a series which looks something like this. Your focus is always on this function right here. If limit as n approaches infinity, this right here, in terms of limit, evaluation does not exist. A limit cannot be formulated. Or if limit as n approaches infinity, that series does not equal to 0 or an does not equal to 0, you have divergence. And that's all there is to it. But what does that mean with regards to the flip side? It means if limit as n approaches infinity, this has a limit which exists, and if limit as n approaches infinity, that series equals 0 in terms of its tending towards or approaching, then you have convergence. But we're focusing here on divergence. You have to satisfy either or over here, and you will demonstrate a divergence for that series. I will demonstrate you some very good examples, and here the examples are fast. We can run through this video fast. Let's look at this one. N squared divided by 2n squared minus 1. This right here is your function from 1 to infinity. You want to apply the test of divergence here? You can. Just take everything here with regards to the numerator and the denominator and divide it. Or you can do the L'Hopital's rule. As n approaches infinity, you'll have an indeterminate limit form. Infinity over infinity, you can do that L'Hopital's rule, the derivative, or just do the easier way. You'll end up getting 1 over 2 minus 1 over n squared. Limit as n approaches infinity, you have here a 1 over 2. In this particular case, an does not equal to 0 because here the an is equal to 1 over 2. Because you're not fulfilling this requirement, you're seeing divergence, and that's all there is to it. This series here would be divergent. Let's look at this example. Nth root of 3, which is no different than you looking at 3 to the power of 1 over n. You're doing the limit evaluation here. Limit as n approaches infinity, does this series tend towards 0 or not? Does it? We'll find out. You're basically looking at 3 to the power of 1 over infinity. You can put this right over here. What do you end up seeing? 3 to the power of 0, which is 1. It tends towards 1. It doesn't tend towards 0. Therefore, you have divergence because here in this case, an is not equal to 0. It's a divergent outcome over here. And you can see the limit application for this specific series here was not hard. We're not going to be expanding out the series here because we're just learning the application of the divergence test. I want to keep this expedited for you all. Let's look at this. You have from n equals 1 to infinity, your series function is arctan. Does this approach in terms of a series towards convergent value or divergent? You would have to do the limit evaluation. Limit as n approaches infinity. Either if the limit does not exist or you do not equal to 0, you have divergence. You were looking here at arctan n. You don't have to do this by any means other than a good graphic way or the calculator. Arctan graph is always pi over 2 and minus pi over 2 horizontal asymptotes, and your graph looks something like that. As your x values approach infinity, your function approaches this horizontal asymptote, and here you know it's in terms of limit you're equaling pi over 2. This value here is not equaling to 0, so you have a divergent series over here. The limit exists, but your series does not tend towards 0. You have a limit value of pi over 2, therefore you must be divergent, and your answer would be good. Let's look at this one. From 1 to infinity, we have cosine 1 to the power of n. You can put your calculator on the RAD mode and actually get a value for that, and let's do it. We have the RAD mode, the radian mode. We do 1 cosine, we have 0.54. In essence, we're looking here at a 0.54 to the power of n. You can do a limit as n approaches infinity. You obviously will have a limit which will exist, and very likely it'll be a convergent item because you can do 0.54 and to the exponent of a very large number. I'm filling in all the 9s, and look what happens. I get to 0. And this right here would be a series which will tend towards 0. You would have convergence. In this particular case, the test for divergence fails. It doesn't demonstrate divergence, it demonstrates convergence. How about this? N equals 1 to infinity, e to the power of n divided by n squared. What is this? Divergent or convergent in terms of the limit? If I'm doing limit as n approaches infinity, I have e to the n divided by n squared. I would put infinity over here. I would have e to the infinity divided by infinity squared. I have a infinity divided by infinity indeterminate limit form. I can run everything here by means of the derivative with respect to the n variable. I'll have e to the n divided by 2n. The L'Hopital's rule procedure, you know that. I'm running this through infinity. I'm still seeing e to the infinity or infinity. I do another round of derivatives, which you can until the indeterminate limit form is exhausted. Here I'm seeing e to the n. Let's bring that back. When you do the derivative of the numerator, you have e to the n. Here, when you bring this back to the 2n, you do the derivative, you have here a 2. And now when you plug in infinity, you basically end up seeing a limit over here. An here tends towards infinity, an here does not tend towards 0. Therefore, this is a divergent outcome. After the first derivative procedure, this is my outcome. When I test it out, after the second derivative procedure, this right here is my outcome. When I test it, I'm still having a divergence. Our next question is this: n divided by natural log n from 2 to infinity, because if you can't put a 1 here, we'll 0 at the denominator, but you can certainly do 2. This right here is your series. Is it divergent or convergent? Do the limit application. Limit as n approaches infinity, you're running it through that natural log in the denominator and you have n in the numerator. If you put infinity over here, you're seeing an indeterminate limit form, infinity over infinity. Therefore, you can run the derivative of each, numerator and denominator. In the numerator, you get a 1. The derivative of natural log n is 1 over n. When you do this, you get an n. Limit as n approaches infinity, this n will really be infinity. That's what you'll have. Therefore, you'll see a divergence. Your limit in terms of this does not equal 0. Limit certainly exists, but it does not equal 0. You have divergence. This is not a hard question and it has been completed for you. Our last one is this: from 0 to infinity we have sine n. You know, sine looks like a serpentine graph, something like that. It goes no higher than 1, no lower than -1, and it's going from positive infinity to minus infinity. We're not continuing this side. Anyhow, sine n, you could have a series in terms of this function. Would it be convergent or divergent? You'd have to evaluate it. Limit as n approaches infinity, you have sine n. For trigonometric functions, you can use the direct substitution property. You can literally just put the infinity here and see what happens. Sine infinity is basically a limit which does not exist, because at the point of infinity, you don't know what value is being adopted by sine. Could you have an output in terms of your function approaching a +1, or is it a -1, or is it a 0, or is it any value in between? Because of that ambiguity, you can say sine of infinity does not exist. The limit does not exist. There's just too much ambiguity as to what value in terms of your function is being approached. At that infinity, it's very hard to clearly or concretely put a value into sine into your calculator and come up with a good value in terms of the range or the output. Hence, that ambiguity leads to limit does not exist. And that's one of the criteria for divergence. Either if your limit does not exist or this does not tend towards 0, you have divergence. It could have tended towards 0 if, for instance, at infinity that specific value was an x-intercept. That x-intercept would signify an output of 0, but we don't know that x-intercept would be the value at infinity. The value at infinity could be any value, and you could have any outcome between +1 to -1, any of these values. Hence, ambiguity leads to divergence here. And that brings us to the end of this particular video. Thank you for watching.